This presentation is dedicated to further describing the problem of denial of service attacks and how do we deal with that on a large scale, including ISPs and web services. So let's start with history. First, denial of service attacks were seen just about the end of the previous century. And in about 5 years, they began to be a serious problem for ISPs and other network entities. In 2015, Microsoft has finally addressed the long-term issues with Windows security by providing a thing called software development lifecycle, which is a methodology towards writing secure code for reliable software. Among all the published concepts, there's a long list of published papers and even books. And among those, there was the STRIDE model, a threat classification model, which provides mnemonic for security threats in 6 categories. It might be used to, for security experts to help answer the question of what can go wrong with a system we are designing. As you can see, there's denial of service in this list in 5th place, but Microsoft security experts meant something else by providing a denial of service here. So the first question to the audience, please raise your hands. Those of you who know what denial of service attack is. Who is able to now describe in a few words what a denial of service attack is? Anyone? Oh, yes, please. Sorry? Great, excellent. First winner. The second question, and what is a distributed denial of service attack? Please go ahead.
When you are sending a lot of information, a lot of data, a lot of requests to one particular server from a lot of different geographic locations, a lot of different other servers that are able to perform the main task.
By saying a lot, how many do you mean? Are 2 locations or 2 machines enough for that? But not 1. Okay, the second winner. But actually, the difference between a distributed attack and not distributed one is complicated. In a traditional meaning, just as you told us, a distributed attack is an attack which comes from multiple sources. There used to be some reason behind this definition back like 10 years ago when the internet was small, but unfortunately no one bothered to strictly define what the word source means here. And the source in this context may be, for example, a computer, like a machine. So if it's multiple machines, like 2, or maybe 2 is not enough, then 3 or 4, then it's a distributed attack. Or maybe it's a 100, so there's no border, no threshold. But if it's a machine, should it be a physical machine or a virtual instance counts? And what if we speak about multiple virtual instances or containers under the same hypervisor, which do migrate in a cloud? So, like I said, it's complicated. If source is then an IP address, if we define it to be an IP address, then it's possible to spoof a single IP source traffic from a number of nodes, say thousands, thus utilizing a bandwidth greatly exceeding capabilities of a lone handling server. Once again, how is it then different from a distributed attack from the victim's point of view? Basically, the idea of telling apart DOS and DDoS attacks based on the count of sources dates back to the beginning of the century, when computational resources, including networking of clients and servers, were still comparable and single-sourced DOS attacks were more or less common. Today, in regard to the mitigation, it's almost useless and almost impossible to tell those apart. And with that in mind, it's more convenient to use a different approach in which a DOS attack, like not distributed, is actually when an attacker generates a specially crafted packet to exploit a vulnerability in a handling server code, like ping of death or something like that. This is exactly what was meant by denial of service in stride model by Microsoft experts. On the other hand, a DDoS attack, a distributed one, is exactly a computational resource exhaustion, no matter the size of the attack. And computational resources may include memory, processor time, network bandwidth, and others. So the basic idea behind the risk management and risk assessment approaches is surprisingly risk assessment. Modeling and management. However, assessing threats is not easy. People are often afraid of scary but unlikely risks, not giving enough attention to real threats, and for risk assessment, it's convenient to use some simple tools like this one, which is a probability impact matrix. And here is how it works. On the vertical axis, there's the probability of the event, and on the horizontal axis, there's the incident severity, how harmful the event would be in case it happens, and how much of a destruction will it cause, and how much it all would cost for a victim. Rare and trivial threats are the ones you most of the time don't care about because you don't have enough time to address this nonsense. And severe and likely risks are the ones you handle first. Then there's a large field between those where you set priorities, plan, and manage. A DDoS attack for an average internet resource is something which is totally dangerous because it might require you to change ISP, relocate to a different cloud or different data center and stuff. But for an average internet resource, it's sort of unlikely to happen. However, there are cases when a DDoS attack becomes much more likely to happen. So here is a list of possible types of motivation of an attacker, ranging from simply fun, through blackmailing and revenge and preventing access, up to market competition, when one of the competitors in the market wants to bring down all the rest of the market to promote themselves, like in Google search results and also on the white market. So if anything in this list applies to a network resource or its dependencies, like a DNS authoritative server, then the probability of a DDoS attack becomes higher. Not everything in this list is under control, but something is clearly predictable. And if anything in that list applies to your resource, then you might want to take care and to prepare for an upcoming attack. So this is for the risk management. Let's proceed to the technical stuff. Let's now talk about classification and categorization of DDoS attacks. Here is a list on the Wikipedia. It's much longer there. And the issue is that with this list, if you are going to choose a solution, you are not sure if future attacks, which, a new type of attack is basically invented each year or maybe even more frequently, and you are not sure about what solution to choose to address future attacks. Also, this naming is, it has some serious problems with name convention and stuff. So we prefer a different approach. So, like I said, network resource exhaustion is basically what is the basis of a DDoS attack, and a computer network as of today consists of layers. A network resource is not available to its users when at least one network layer fails to provide service, and a DDoS attack can be attributed to a network layer which it affects. According to the OSI model, here is a list of layers, and here is a list of network resources that might be affected by the DDoS attack on each layer. Having layer 2 in this model, by the way, is important because it highlights the difference. We are not speaking now about ARP-based attacks. We are speaking strictly about DDoS attacks, which bring down a single link or a single network route, which actually might happen if network equipment is configured in a certain way. So what we are going to do next is to go down through all of those types and to see what attacks are common for each of those layers and how do we address the issues with those attacks. We start with the lowest layer of OSI model, and there's a long list of attacks related to low layers. But the most probably important here and most widely known is amplification. What's an amplification DDoS attack? In a nutshell, most servers on the internet serve data to clients, and they usually send more data to a client than they receive from them. This is okay for TCP-based servers, as the TCP protocol has a built-in mechanism called triple-way handshake for verifying the remote IP address of a client. However, there's no such mechanism present in UDP, and each author of a UDP-based protocol must design their own handshake, and sometimes they just omit that in a design phase. Thus, an attacker is able to impersonate a victim by spoofing source IP address and to send a request for a large portion of data on behalf of the victim. An attacker will generate, say, 1 gigabit of requests, but the victim will receive like 30 gigabits of responses, which may impose serious consequences for the link congestion. There is a long list of protocols vulnerable to amplification. Those are mostly obsolete protocols like Routing Information Protocol version 1, which is ancient. But there are modern protocols as well, such as gaming. And as it's mostly obsolete servers, they eventually get updated or replaced or just thrashed. And thus the amount of amplifiers we see on the internet is steadily declining. However, once in a while, a new vulnerable protocol is discovered, and the number of amplifiers on the internet skyrockets at that moment, and then it starts to slowly decline again. The amplification factor is how much data you can basically get in return towards the victim from an amplifying server compared to the size of a spoofed request. There's also a stable downtrend in terms of available amplification power, and the factor is quite different for each protocol, NTP being about 10 times more powerful than LDAP, according to the NIST report. Most amplification attacks are easy to fight with for an average ISP because the source UDP port is fixed, so basically, it looks like you can just use a simple bit mask to track down and filter packets which come from a typical amplification port, like 1, 2, 3, 4 NTP. And moreover, there's a mechanism which was developed by IETF, you can use to actually order that filtering from your upstream connectivity provider. It's called flow specification rules. This is a part of BGP. RFC 5575. Using flow spec, you can notify your upstream provider then that you don't want to receive, say, packets from a particular UDP port, which comes in handy when you face a powerful amplification attack. However, there are at least two major problems with flow spec. The first one is obviously SMP amplification. The other one is when an amplification attack doesn't actually have a fixed UDP port. Also, a lot of ISPs just don't want to provide a flow spec service to you because it's heavy in terms of computational power. Here is a recent example. There's a story from this February about memcached DDoS attack. Who have heard about it? Okay, great. I'll go through that in a fast fashion. So memcached is essentially a database and an in-memory key value store. So it's often used as a fast cache. So a long time ago, memcached authors made a huge mistake. They made memcached listen on all network interfaces, including externally facing ones by default. There are a lot of machines on the internet still with port 11211 UDP open, and this port is memcache ASCII protocol listener. This basic ASCII protocol was meant to be used on a loopback device only, or in a local secure network at most. It doesn't do any authentication, and this weakness is known for long. Like 4 years ago, Ivan Novikov from Well-Arm has discovered numerous methods to exploit memcache ASCII protocol. And in November 2017, a new threat emerged. Security researchers Shangbao Kai, Zhang Lu, and Li Fu have discovered a way for an attacker to use this ASCII protocol to send large portions of data from memcache memory towards a victim. Here is how it works. This Python code snippet is all you should do to inject an arbitrary value into a memory of a remote vulnerable memcached server, here by the name reflector.example.com. And the value may be of an arbitrary size, up to a few megabits maybe. For the sake of DDoS amplification, this snippet should be run only once. And then the attacker needs to send packets towards that server with victim's IP source address and a proper payload, which memcache will treat as a correct request. Here is how the payload is structured. This is, again, all an attacker needs to do to send a large portion of data they have put before. The value of A is reusable. Moreover, what's even more convenient for web developers and disastrous for internet, the gets method accepts multiple arguments. So here's what you can do to send the value 5 times in a row, multiplying the attack traffic 5 times, or 10 times, or 100. More than 100 doesn't fit a packet because of MTU size, but 100 is still enough. Like in Red Hat, memcached listens on all network interfaces, and also it's the same thing goes for Zimbra, etc. Red Hat engineers, I guess, they offer some Linux-based handling for that port, but most of system administrators are just switching Linux off, but so this doesn't work in all the cases. So the amplification factor, like I said, is how much data you can get in return, and our previous champion was NTP with amplification factor as high as 557. But for memcached amplification, in theory, the factor would be like millions. But in practice, all the packets of the response aren't sent at once. And in practice, we see an amplification factor close to 9 to 10,000, which is still 20 times our previous champion NTP amplification does. So amplification attacks were thought to be something more or less under control before. However, as practice shows us, they are not something to underestimate. I won't go into details here. Here is a snippet by Job Snyders from NTT, how you can rate limit amplification sensitive ports in Cisco IOS XR. One important thing here is you may wonder why an ISP can't just drop all the traffic to and from port 11211 altogether because it's not used in production. The reason is it strictly contradicts with the concept of net neutrality, while rate limiting some suspicious network traffic apparently doesn't. So if you're an ISP, better speak to your lawyer before. It's always a good idea to speak to your lawyer, by the way. So for newly designed UDP-based protocols like a new ITF design, which is quick, it's a must to include a proof of source address ownership. So in quick, source address of a client is always validated, and the initial handshake packet is padded with empty bytes up to 1,280 to make sure that there would be no amplification factor whatsoever. This is what we expect other UDP-based protocol developers to do, actually, but you know. So a lot of floods are always also attributed to that layer, and also IoT attacks, which you might have heard about. So there's a long list of different botnets. The Mirai botnet, which is famous, which is like a 2-year ago incident. The Mirai source code is published on GitHub, and it's frequently used as a framework for writing new botnets for IoT. There's a long list of other botnets which are based on Mirai, but for the practical defense, the name of a botnet is totally irrelevant, though. So yes, and also infrastructure attacks. We'll speak on that a little bit later. So with regards to mitigation here, from a victim's perspective, you must have BGP Anycast network with multiple points of presence, multiple scrubbing centers with enough inspection power. And also, you need to do inventory management to drop the traffic vectors you don't want to see coming through the border of your network, like UDP towards an HTTPS server. You may want to rate limit less important traffic, like maybe your corporate network traffic or stuff. And also, you may want to do some challenges and handshakes. We'll cover that a little bit later. But from an ISP's view, so from the view of network provider, which is providing you network services, what they can do with their current equipment is basically simple heuristics against typical amplification attacks and other floods. And in case those heuristics don't help us a lot, an ISP will just put all the traffic towards that victim to a black hole and let the customer take care of it themselves. This is basically what threat model of an ISP. Here is how it looks like. So let's proceed to the transport layer. And on this layer, we see attacks related to the only complicated transport layer protocol, which is on the internet for now, which is TCP. One important thing here is that, as you can see, SYN flood might be affecting both transport and network layer. And affecting multiple layers might, in fact, be the attacker's purpose. I mean, say, an attacker is generating NTP amplification and SYN flood at the same time. So for a couple of days, a network engineer of a company is basically handling NTP amplification because it's something that is seen in TCP dump and monitoring engines. And after 2 days, when the NTP amplification is successfully handled, it turns out that it's the scene flood part of the attack, which actually is causing downtime. So the idea of combined attacks is to divert attention of people who are in charge of mitigation and to prevent them from focusing on the real threat from the moment one. By the way, probably the main issue about IoT was not the bandwidth of attacks. We knew long before that such attacks would be possible in the future. But the ability to implement full TCP, GRE, or even HTTP flooding, which wasn't common before IoT attacks. So with regards to mitigation, what you can do is, against scene flood, you can do a three-way handshake-based scene proxy, allowing a victim to verify the source IP address. Here is how it works. Here is the typical triple-way handshake towards the server. And if you get a lot of scene segments here, then your connection table will just explode, or even your bandwidth will come to a complete shutdown. So to address that issue, you put a traffic filtering node with enough inspection power and bandwidth, which basically responds to scene segments, so connection requests, and allows the handshake towards the server only when it's successfully done to the traffic filtering node. So the source IP address is verified using the algorithm called scene cookies. Once you have done that, you have verified the source IP address, and you can do session analysis, heuristics, and block list also. Here is the story about those block list thing. So this is a true story. One enterprise has got about 40 gigabits of DNS amplification and decided it's a good idea because, you know, a DNS amplification comes from vulnerable servers, from their own IP addresses. So it might be a good idea to put the IP addresses of those vulnerable servers into a block list. So the enterprise decided to parse the source IP addresses from TCP dump and populate a block list. Within 2 hours, the attacker started enumerating all the IPv4 family address space in the internet, which is about 3 billion IP addresses, not including private networks, within empty packet sources coming from UDP port 53. And the attacker started with most popular ISP access prefixes in that country. And 8 hours later, nothing is working, 1 billion IPv4 addresses in block list, and all the Juniper equipment they were using is completely unresponsible. So it is dangerous to use either block lists or allow lists without source IP address verification. Also, don't forget about inventory management once again. And an important slide here that those attacks might target not only servers, but client networks as well. Some real-world scenarios from our practice include gaming, betting, altering results of online exams in United States universities to prevent competing students from collecting good marks. Stocks and auctions, and also this incident with European Commission. I'm providing a link. You may follow it, because I guess the slides would be published on the conference website. Defense is basically the same, but scalability is a problem because you have to track all the outcoming TCP connections and then distribute that to a large number of nodes. So one important remark is today it's wrong to believe that layer 4 is only TCP. UDP doesn't matter a lot, but new protocols are being implemented. So you might want to update your solutions as those protocols are discovered. And yes, here is a method called blocking known attack sources. You may find it in best practices. It's also known as I'm not expecting Spanish Chinese customers. So why don't we just deny access to like Chinese IP addresses or other countries' IP addresses? Here is why it's a bad idea. Even if we prefer to just stick to the technical point of view now, there's quite a few drawbacks of such an approach. The first is geo-IP databases are unofficial and unreliable. Here is a simple example, MaxMind geo-IP database. And let's look through the data it has for the Google DNS servers. And it doesn't tell us the city or the region, but it does provide us with one thing, which is GPS coordinates here. Let's look through those GPS coordinates. Apparently, that's in the middle of a lake. So a DNS server went underwater, and still no arrests. How come GeoIP database? So this is wrong because Google DNS is anycasted. It's not located into a single region. It's located in different parts of different countries. Also, GeoIP database always has its own owner location versus actual data center location dilemma. And basically, GeoIP database is unreliable for anything except statistics, because there's no geography on the internet. None of RFCs mention geography and countries, only network topology. And on the internet, there are no countries, just autonomous systems and their relations. So, but not only databases are unreliable here for that particular task, because for statistics they are good. But IP addresses, IPv4 addresses get sold and bought, and some IP networks are being used very far from the original internet registry, like they are assigned to APNIC for a Malaysian company, but they are used in Europe. And also Anycast. Some of the above might be better with IPv6 because, the IPv6 addresses won't get bought by anyone. There's plenty of them. But IPv6 adds its own problems. With IPv6, as you know, it's possible to address each atom on the Earth surface. But it's impossible to store a large number of entries in memory. So like 10 years ago, blocking whole IPv4 networks was already considered a bad practice, but with IPv6, this method has no other way than to return. Welcome back to the amplification-specific flood. So this is, we are speaking now of attacks which are targeting application layer and actually HTTPS applications. The first example here is WordPress pingback. The attack is using the attacker using that method is forcing a vulnerable WordPress installation to issue HTTP or even HTTPS requests towards a victim, with like millions of those installations still available on the internet. An arbitrary attacker is practically capable of generating a few gigabits of just TCP segments using this method, and up to a few dozen gigabits of a total attack. The WordPress installation, when it receives such a request, it starts a new request for the example.com. And the source IP address is, the source port, sorry, is always different, so flow spec is of no help to us. And for a TLS-enabled resource, the only information enough to reliably tell a WordPress server from a legitimate user is encrypted. So most of the time, you need to disclose the encryption keys to your DDoS mitigation provider or put them directly into a handling machine. There are also solutions which do not require you to disclose your encryption keys, but they require a slightly complicated setup involving, with Nginx, involving setting up a syslog server and streaming the access log of your HTTPS server through syslog towards the DDoS handling instance. Another example of a layer 7 attack is so-called full browser stack. So a bot can actually be much more clever than a simple WordPress script. And advanced botnets are capable of using a headless browser, Internet Explorer or Edge or Chrome, and to make use of all the JavaScript engines and image handling, font handling, and the bot is able to basically go through even complex challenges like JavaScript code execution or page rendering. CAPTCHA is a weapon of last resort against full browser stack when we speak of active countermeasures. And it has a couple of advantages. It's easy to implement. ReCAPTCHA is available for free, for example, and generally it might work in most of the cases. There are also drawbacks of this solution. CAPTCHA requires you to inject some scripts, some images into your user experience, which may break the experience of your users. It breaks mobile applications which are not designed with CAPTCHA in mind. Sometimes CAPTCHA is harder for humans than for robots. I don't know what's the first word here. Also, not all bots are malicious and not all humans are innocent. There are CAPTCHA proxies and farms which offer solving CAPTCHA images for a slight amount of bugs using automated humans. And also, malware is able to inject CAPTCHA into pages a user of the infected computer is looking at. So there would be actually a human solving the images. Also, OCR tools evolve very fast. And to make your CAPTCHA more user-friendly, you need to do also voice challenges to address all of your customer base. And voice recognition evolves even faster. And the last issue here is that actually an open-sourced CAPTCHA is relatively easy to break using open source machine learning tools. If you are interested in that, if you want to hear more about it, so just find me today's evening or tomorrow, and I'll show you the actual code of how it could be done. So CAPTCHA is now security by obscurity. If it's letters, then the CAPTCHA should be closed sourced, and if it's like images of booths and cars and houses, then the image base must be large and must be hidden from the attacker. And under most conditions, full browser stack botnet won't cause any link degradation. So network operator believes that it generally falls out of scope of its responsibility. Also, the traffic is encrypted, so the network operator it's not able to do anything with that. Another example of a layer 7 attack, DNS. DNS is built on top of UDP. There's an asterisk here because, okay, we'll cover it later. And a DNS request fits in a packet. The structure of a DNS query is simple. So here is basically all you need to do to retrieve the IP address for Facebook.com. That's about 100 of a little bit yeah, 56 bytes for the request and 72 bytes for the response. So an attacker is capable of generating simple spoofed requests, queries, which will make a user space DNS amplification process all those fake requests, rendering a DNS server unavailable on the layer 7. This is one type of such an attack is called water torture, and this is what happened 2 years ago with Dyn, for example, when Spotify and Twitter went down. On a bright side of things, DNS protocol allows switching to TCP, and in TCP, as you already know, we have handshakes. So block lists apply, but once again, enough bandwidth and inspection power is strictly required to handle this. Unfortunately, all other UDP-based protocols are mostly built without DDoS mitigation in mind, so do not allow TCP switching. So for the mitigation, it's complicated. For the active phase, you may use JavaScript challenges and CAPTCHA, but we've discussed that before. Sometimes they are of no use. And for passive stuff, you may use application session analysis, tracking down your users, machine learning, and monitoring, but it's complicated to implement it. This is a mandatory slide. When somebody speaks about machine learning, this is a mandatory slide. Because everything which is machine learning based is not strict. There are two common problems with artificial intelligence, false positive and false negative. Basically, any algorithm may be turned to either 0% of false positives or 0% of false negatives. Like, even broken clocks display a correct time twice a day, if those not Apple Watch. So the truth is somewhere in between. So your business your business guys need to define the balance. How many users could be affected in case of an attack and in case there's no attack happening? This is the complete classification, which is mutually exclusive and collectively exhaustive. So you may just use it to evaluate all the solutions you might deploy for the DDoS threat. So this is a basis for due diligence of the solutions. However, as you may know, internet is a complex thing. There's a decades-old job interview quiz, which goes like, what happens when you type www.google.com in your browser? There's a GitHub repo which addresses this question with a long list of answers, point by point. And with regards to network, there's a list of something happening on the internet when you try to reach a resource. This list, by the way, is not complete because today you have a lot of things like load balancers and deep packet inspection and also TLS stuff like CRL or OCSP. In case you have a must staple in your TLS certificate, in case an OCSP server goes down, your service basically after some time won't be available for users. Also CDNs. So as the Dyn incident with DNS shows us, an application server could not only be a direct target of a DDoS attack, but also might be an indirect target, and any dependent service could also be affected. So each step here could suffer from an attack, ranging on all the network layers. So once again, it's crucially important to do inventory management. and to do infrastructure monitoring to know where your weakest points are. From the architectural point of view, the security is not a product, not an appliance, it's a business process. And the ability of DDoS mitigation must be built into the design of any protocol. I can't stress it further. And a concerned company must follow policies, frequent updates, risk management, incident handling. Yes, for a cloud, so a network operator will basically suffer only from bandwidth consuming attacks. Sometimes, if it's a cloud, what's added is CPU or memory costs. But anyway, the probability of an attack towards the network is the aggregate probability of an attack for each customer. And the most easy way to handle it is just to get rid of a problematic customer. And for the customer, there's the rest of risk management. For a network operations team, for a systems operations team, it's important to stay aware of public relations activities, marketing activities, and news to know where the risk is higher and when it's lower. And even more important is to choose a solution given strictly all the layers and risks. As the example with Memcache shows us, it might take 3 months starting from the disclosure of an attack, of a vulnerability, up to attacks in the wild. So 3 months are an overly short interval, but next time it might be even shorter. And as Meltdown Inspector show us, the embargo approach, where you do not disclose vulnerability until it's fixed everywhere on the internet, doesn't work well for a community large enough, like an ISP community or HTTP application community, if there's one. So the problem is not Internet of Things only, it's the overall insecurity, operational failures, and ignorance of some Internet community members. Sounds like we have found the root cause, which is ignorance, but it won't go away anytime soon. So, to handle it, you may want to do collaboration with other network entities, with your upstream network and connectivity providers to ensure proper and timely reaction to a new threat. If you have a contract with CSIRT or CEIRT, and I hope you have some, frequently reach out to them for an advisory and make sure they will notify you in case something really bad is happening on the internet. So that's it. Here's my email, but I want these two to stay here on the slide. Let's proceed to the questions you might have, and thank you for listening. Any questions? Yes, please.
Do you have any stats on how much ISMs actually allow spoof traffic, spoof source IPs to go through and how it develops over time?
So the question is how many ISPs or autonomous systems on the internet allow spoof traffic from through their network. The idea is that for a transit provider, there's no easy way today to get rid of a spoof traffic. If it's a stub autonomous system or if it's an endpoint autonomous system, it may do something about it. But for a transit provider, it's complicated in terms of computational power, and also complicated in terms of mechanisms which might be used to address this. BCP38 does not work. ITF is now trying to develop something else instead of, or in addition to BCP38. But still, I believe that most of transit providers actually allow spoof traffic. Also, a lot of clouds do that. Not all of them, but I believe Amazon doesn't allow you, but maybe Hetzner may allow the spoof traffic. So it's still a huge problem, and will be such for a long time. Yes, please.
What are the GeoIP providers that you think provide the best database out there?
Which GeoIP database may provide you with best data? I would recommend. So look, like we are providing services in different parts of the world. And in each part of the world, we are using a number of GeoIP databases collected from local players. For Asia, I may recommend ipip.net, I guess. ipip.net, yes. This is a Chinese company which is providing a very good GeoIP database. For other regions, you may reach out to local community to find out if there's some data better than MaxMind. Once again, MaxMind database is good for statistics. But if you are going to apply it for some decision making, you may want to use not only one database, but you may want to combine different databases into a single solution. Yes, please.
You told us that volumetric attacks were going down. Do we also have time stats for instance, silver attacks? Are they going up, down, stable?
Amplification attacks do a number of amplifying servers goes down, but for amplification attacks, there's only a slight downtrend, and the most prominent threat after amplification attacks is actually layer 7 attacks. So it's not about with SynFlood. We see it accounts for, I guess, less than 5% of the total number of incidents. There's also SynAC attacks. So we have plenty of time, right? Here's a bonus track. Yep, there we go. Part of this was incorporated into the tutorial, but this is a presentation about wrong methods. This is my favorite band, which is Depeche Mode. The first part is about using block lists only where they are applicable. So we've seen that. Oh no. That's it. That's the point. So say there's a SynAC attack, which is different from SynFlood, but I'll tell you how. So there's more than 100 gigabits of TCP traffic coming with 2 flags, synchronize and acknowledgement turned on, and it's too much of a bandwidth for an average resource. So you might want to use flow spec, like match TCP flag and drop the traffic. So here's why it's a bad idea. And if there's anything I like about Internet of Things, it's the opportunity to post the Mirai source code, the source code of an actual IoT botnet as proof. Here is the SynAC flood generator code. This is all you must do. The packet is 60 bytes long. And this is all you need to do for the TCP part. Also, you need to fill in IP header, but it's also small. Here is how it's different from scene flood. What one bit is flipped. So the question is why there exists scene-ACK flood, scene-ACK reflection instead of just scene flood? Because it's the same packet size, no amplification possible, same packet structure, and the packet is spoofed anyway. So you can't be even sure this is a reflection. So apparently there's no benefit whether it's scene flood or scene-ACK flood. No, there is. Some networks are responding to TCP connections, like a data center network, or your application servers are responding to TCP connections. But others, like enterprise networks, are generating them. So scene flood is harmful for the former, but scene-ACK flood is like a nuclear weapon against the latter, because no challenges are possible against scene-ACK flood. And also the SAD flow spec rule is basically of no use because it will drop your legitimate traffic altogether. Sometimes the attacker just don't care whether the network is generating or receiving connections. So sometimes they forget to switch the flags. But anyway, both types of attacks are possible, and for the application servers, we frequently see scene flood. But like I said, it accounts for less than 5%. But still, there's such a type of attacks. And also, we see sometimes scene-ACK reflection. That's mostly targeting enterprise networks. Do I answer your question? Okay, good. So, yes, so that's probably it for this presentation. So, any more questions? Yes, please.
So if captures are not really good or suboptimal, do we have any other alternatives? Like what can you do instead of capture?
Yes, for capture. Let me find this slide. Yeah. So for as I promised to do it. So sorry. Yeah. So this is, by the way, the code, and this is a link. Sorry. Yes. This is a link to the source. I will add it to the presentation, okay? So this is the code which is used to, this is the actual captcha we're going to break. Here is all which is related to image recognition. So the first thing is you generate a large number of characters using a library if it's open sourced. A large number like tens or hundreds of thousands. For each of them, you know what you were generating. So you have an image, you have a letter. Here is how you find the contours and thresholds to actually locate the region of each letter. And then you use deep learning, convolutional networks. Here is how it is done with Keras, which is also an open source library. So you add two convolution layers with pooling, and here's also a hidden layer and an output layer. And then you train your model. And after the model is trained and it's stored on your storage like SSD or hard disk, it might be large, by the way, but still, here is what you need to do to parse the images. So I will add this to the presentation, which will be on the website, no problem. So also the second link, which is very good, I like it. It's describing deep learning in simple words. But the basic idea is that Let me go back to that slide, which is, we are almost there. Yes, there we go. Basically, asking a customer to go through some challenges is, we don't have any better solution now. Like I said, artificial intelligence it's not a magic, yes? It's simple math, but it's a part of math which is heavily evolving because it's a lot of enterprises want machine learning to be deployed and they want artificial intelligence to happen. And I personally believe that in a couple of years, maybe 2 years, we'll see all those libraries, machine learning libraries and tools built into a browser. So a browser will be able to solve something here. So for future applications, as I believe, we don't have to treat humans and robots differently, because there will be robots. Like no one is now typing an HTTP request in a command line. They're using browsers for that. And also there will be tools for different approaches, like automatically registering you on a website or automatically downloading something. So the good approach here, if you ask me, to treat not the capabilities but intentions. What is this person doing? What are they going to do? And what do they want to do? Either break your resource or to have some information, to have some business together. So I don't know if it's a response, but here's what I can do. Yes, for the record, the question was what can we have instead of CAPTCHA, like the new generation CAPTCHA? Sorry, apparently there's none. Please go. What do we say about solutions which do remote client fingerprinting, like tracking down headers and ciphers and some maybe threat intelligence? It has its own regions of applicability. If you take reCAPTCHA, you are not required to actually solve a CAPTCHA on each occasion because Google maintains a huge database of IP reputation. For regions far away from United States, like Canada, this solution might work a little bit in a suboptimal way, and also it treats Tor network as a bad one on each occasion. So there are some complications with it, but once again, when you don't speak about full browser stack attacks, and you don't speak about mobile applications, those solutions have its own, regions of applicability. The issue with mobile application is, sorry? So I'm now speaking about one certain thing, which is mobile applications, because an attacker is basically able to download an APK from Play Market and to actually use it for attacks, or use the same library, because how is the botnet designed? An attacker just Googles some library, which is like on GitHub, and is using that for malicious purposes. How does an average mobile developer do the same thing? It does it in the same fashion. So sometimes the same library is used for botnets and for mobile applications. So regarding remote fingerprinting, I believe you may use it for up to 80% of current threats, maybe even more. But if we speak of a not so distant future, then maybe at 80%. The rest of it is mobile applications, and also if you deploy statistics and correlation engine which is good enough for you, if you know what your customers are supposed to be doing on your website, then you may use fingerprinting for less threats because there would be less false positives. Thank you. More questions? Yes, please.
Do you have any insight into how the DDoS is happening in the MQTT world of IoT?
In what? Sorry?
There's a base level protocol MQTT, which is used heavily for IoT devices.
So DDoS against Mosquito, right? We haven't yet seen some. It might happen, but we've never seen some.
I think the problem is the library not supporting.
When you speak about IoT, one important thing always is attribution, which comes down to authentication. So if your authentication engine is powerful enough and able to handle it, also if you are able to go with some tools ranging from fail to ban up to complicated solutions, to make sure that if some remote device has failed authentication for a number of times, then it won't be allowed access anymore. If your IoT device is required to be authorized on your network, then you might have less problems than others. But there are also cases when you have no authentication. Yes. Yes, also private VPN, and for a VPN, if it's possible, it's better to use something which is not related to IP networks like MPLS. If your provider is able to provide an MPLS VPN to all of your sites and all of your devices, it's a good thing. Yes, it's a telecom level, but yeah. Like I said, you need to communicate with other network entities. So that's it. Congratulations. That's the end of the first day. Thank you.